In general, the kind of year we're going to experience gets its label at the end of the year. In 2005, well, that was the year of the never-ending hurricane season. 2017 was the year we experienced an eclipse and lost Cassini. 2020 was the year satellite constellations went from a handful to hundreds of spacecraft. 2022, that was the year of Mars exploration with Curiosity, Percy, Ginny, Insight, and Tianwen-1. Each year gets to define itself, and it is up to us to fight or embrace what that year brings us. This year, 2023, is still young, but I'm going to hazard to guess that come January 2024, this will be the year of Io. It may be the year of many other things, but Io will be on the list. Right now, the Juno mission is circling ever closer to Jupiter as it migrates inward. It is passing by moon after moon, and right now, every 38 some odd days, Juno is swinging past Io on a progressively smaller and smaller orbit. The closest approach will be in December, but the lead-up images are going to be more and more amazing. And tonight, you're going to get to meet another member of our team, Beth Johnson. She is our planetary science expert, and she'll be on camera interviewing Io expert Julie Rathbun. Their conversation is going to take you on a whirlwind tour of why this moon is worth your excitement and touch on how you can get your eyes on the images. Before we get to the interview, it's black hole time, with news on black hole formation, our Milky Ways, supermassive black holes' feeding habits, and new models for when black holes collide. And we're going to ground ourselves a bit in some good old-fashioned space rocks, including news of a newly found crater in a French winery. We're going to bring you all of this and more, right here on Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Before we get to black hole news, I want to take a moment to say black holes, at the most simplistic level, are nothing more than objects so dense that to escape their vicinity, you have to go faster than the speed of light. And since nothing can do that, nothing can escape a black hole. It all comes down to forces and motion. To leave Earth, you need to accelerate away faster than gravity pulls, or you need to fire yourself off the planet with an initial velocity of 11,200 meters per second. At that speed, you could either race from the North to the South Pole in 20-ish minutes, or you could take off straight up, and while gravity will slow you down, it won't be able to reverse your direction and bring you back to Earth. Now, here is where things get weird. If we make our Earth half its size in radius, but keep the same mass, you'll be closer to its center of mass, and the pull of gravity will go up. And you'll have to go 16,000 meters per second now to get away. Make it 1/10 the size, now you have to go 35,000 meters per second. And if the Earth's mass is somehow compressed all the way down to the size of a grape, you will have to go the speed of light to try and fly away. But you can't. Nothing with mass can go the speed of light. And that's how it works at every size scale. If you take any amount of mass, no matter how small, and You can press it down tight enough, you can make an object that has a surface nothing with mass can escape from. Most black holes we know about are made of at least enough mass to make a few suns. We call these stellar mass black holes. And we know of supermassive black holes with billions of times the mass of the sun. The one and only thing that makes them all black holes is that simple fact. To fly away from them, you have to go as fast or faster than light. And since nothing can do that, they sit there darkly holding on to their secrets, and we have no experimental way to fully understand what is going on inside their radius of no return. While we can't watch anything return from a black hole, we can, however, watch things fall apart as they fall in. Researchers learned how to image the areas around our galaxy's supermassive black hole about 25 years ago. In 2020, Andrea Getz and Reinhard Genzel received Nobel Prizes for their separate teams' innovations that made these observations possible. And now, with those couple of decades of data, we are starting to see how our black hole can change things over time. In a new paper published in the Astrophysical Journal, researchers led by Anna Kurlow document how one cloud of gas has been stretched out by gravity over time. In 2002, it appeared as a normal blob of mass. The cloud is estimated to have about 50 Earth masses of material, and it has an orbit that would repeat every 170 years. But repeating means the blob would need to survive. It is unlikely to survive. In 2036, this cloud will make its closest approach to the black hole, and it is expected to fall apart into so much scattered gas. Over time, that material will fall toward the black hole, and we may get some flashes of high-energy light as it takes its final dive into the great place of no escape. And if you're wondering how a random cloud of 50 Earth masses of gas got to the center of the Milky Way, the answer is actually kind of cool. According to Kurlow, quote, "One possibility is that X7's gas and dust were ejected at the moment when two stars merged. In this process, the merged star is hidden inside a shell of dust and gas, which might fit the description of the objects. And the ejected gas perhaps produced the cloud-like objects." While black holes can and maybe do come in all possible sizes, it is super hard to find things that emit no light. The few times we've had definitive observations of a black hole of several to several hundred solar masses, we've observed the black holes using gravitational waves, not light. Just like the energy of two cars crashing generates sound, the energy of two black holes crashing and merging into a larger black hole can send waves of energy through space. Only sound doesn't carry in vacuum, and the waves are actually distortions in space-time. We humans are just small divots in space-time that sometimes get distorted by these waves, and we don't notice, and I'm glad we don't notice. And while we don't notice our body change, scientists can measure the distortions that occur on kilometer scales as our entire planet is contracted and stretched. And just like the sound from a car crash can tell you something about what happened, the way those waves stretch and contract our planet can tell us about the black holes. In a new paper in Physical Review Letters, a team of 14 researchers, led by Keith Mittman, released a suite of new models that describe what we can expect to detect in the ring-down of different kinds of black hole collisions. This paper looks in particular at the ways waves can merge together and the ways that can cause the resulting wave to be more than just the simple addition of the two original waves. These models are somewhat perfectly timed. This March, LIGO, the main North American gravitational wave detector, will turn back on for the first time since March 2020. These new models will allow them to get as much as 10% more accuracy out of future detections. As co-author Leo Stein puts it, quote, "We're getting ourselves ready for when we're going to be gravitational wave detectives, when we'll be digging deeper to understand everything we can about their nature." End quote. LIGO and its sister projects like Virgo and Cogdra are helping us understand middling-sized black holes in the nearby universe. And other telescopes let us see what supermassive black holes at the edge of the universe are doing. Using the Atacama Large Millimeter Array, astronomers detected the signature of a supermassive black hole in a galaxy whose light has been traveling for billions of years to reach us. Cataloged as COS-87259, it's massively forming stars and appears to have an actively feeding supermassive black hole enshrouded in cosmic dust. When I say massively star forming, this system is forming stars at about 1,000 times the rate of our galaxy. And it was doing it when the universe was just 5% of its current age. We really didn't think this could already be happening when the universe was just 750 million years old. And if this was just one detection from one telescope, we'd be able to say it was a weird one, a rare one, something unusual and special. But the JWST has also been finding massive galaxies. Galaxies that were already massive when their light headed our way 500 to 700 million years after the Big Bang. According to researcher Erica Nelson, quote, "It's bananas. You just don't expect the early universe to be able to organize itself that quickly. These galaxies should not have had time to form." End quote. In a new paper in Nature that Nelson co-authored and that was led by Ivo Labe, researchers identify 6 candidate galaxies that appear to be 1 trillion solar masses. These are just galaxy candidates identified from images with estimated distances that come from their colors. Follow-up spectral observations will be needed to confirm their distance and their identities. Still, it is looking more and more like galaxies got their start earlier than anyone ever thought. It's an interesting time to be interested in black holes. After a break, we'll be back to look at wet asteroids and other icier science. Stay tuned. Very few things are pretty much the same no matter their size. Asteroids, for instance, undergo amazing changes as we go from looking at small objects, which are rocks, to looking at objects large enough to have had internal heat flow and geologic processes. Asteroids are one of the most diverse classes of objects, in my opinion. I'm sure that the same argument can be made for many things, but today I'm going to say asteroids are remarkable in just how different one can be from another. Asteroids from the inner solar system experienced a ton of heating from the sun, and that changed them. And asteroids from further out, well, researchers led by Dris Tekar just identified a new population of asteroids that seem to have formed in the outer solar system and migrated inwards over time. These objects are similar to Ceres in composition and have the same kinds of minerals that can only have formed in the presence of liquid water. There are also very low-density asteroids, and that seems to indicate that these objects preserve the fluffy mix of ice and dust that came together and in more violent circumstances combine to form planets. This is essentially leftover stuff, unprocessed, uncondensed, that allows us to see what the stuff of planets was like before it was heated and smashed. According to research collaborator Mario Treloff, quote, "These are the remains of the building materials from which the planets of our solar system were created 4.5 billion years ago. In these small bodies and their fragments, the meteorites, we find numerous relics that point directly to the process of planet formation." End quote. Well, we don't have any missions to this part of the solar system currently planned. Missions going to Jupiter or any more distant planets have to go through the asteroid belt. I hope that in the not too distant future, we'll have more data on this newly discovered family of pristine asteroids. The story of planetary science is shaped by rock and ice, the flow of heat, the energy of impacts, and the pull of gravity. It all sounds so simple, really, but then we go and discover worlds like Enceladus, one of the moons of Saturn, that seems like they should be boring, but Enceladus has geysers, and that makes it anything but boring. Eruptions of its geysers were studied by the Cassini mission during its long period orbiting Saturn. And a new research study led by Ashley Schoenfield and published in Nature Communications asks, how exactly do geysers on an icy moon happen? And why is it the eruptions are full of tiny icy silica particles? Their answer is pretty cool. As Enceladus changes its distance from Saturn, it squishes and expands and squishes and expands ever so slowly. And this movement causes its rocky core to heat, and this heat is released by deep-sea hydrothermal vents that may not be too different from the deep-sea vents we have in our own oceans. This heat at the bottom of the ocean can then drive currents that circulate the water. As Schoenfeld explains, quote, "Our research shows that these flows are strong enough to pick up materials from the sea floor and bring them to the ice shell that separates the ocean from the vacuum of space. The tiger stripe fractures that cut through the ice shell into the subsurface ocean can act as direct conduits for captured materials to be flung into space. Enceladus is giving us free samples of what's hidden deep below." End quote. While we only have clear evidence of geysers on Enceladus, there are also hints in the data that Jupiter's moon Europa may also have geysers, accompanying its ice-covered oceans. As for life, I can only hope that we'll figure out how to robotically search for it in my life. It could be there, living in the oceans of these moons. Or there could be nothing. And not knowing drives us to do science. For now, the best we can do with Europa is work to understand everything we can from the images that were previously captured by the Voyager missions and the Galileo space probe. One of the more curious features on Europa is its reddish stripes. It has long been suspected that this is some kind of frozen salt water, but the way the stripes reflect light doesn't match any previously known substance. But when there is a puzzle to solve, researchers get creative and start making things that were never previously known. In a new paper in the Proceedings of the National Academy of Sciences, researchers led by Baptiste Journoud describe what happens when you take water and you just keep adding salt at a very, very low temperature. It turns out that it's possible to make a crystal that is kind of a hybrid of water ice crystal and salt crystal. And these structures can have two salts, that's two sodium chloride molecules, for every 17 water molecules. It's also possible to make one that has one sodium chloride for every 13 water molecules. And these weird new structures called hydrates may be just what Europa has on order. These new icy, salty structures require extreme cold and form in high pressure conditions, such as scientists think should exist in an ocean beneath 5 to 10 kilometers of ice. They also found that even denser ices may be possible. The team's next step is going to be to collect a larger sample during future experiments to verify that match with what we're seeing at Europa. If it does match, we now have one new set of weird salts to look for as we explore moons and as we consider what else might be out there on worlds orbiting alien stars. After this next break, I'm going to hand the show over to Beth Johnson, a planetary scientist that has so far always been behind the scenes here at EVSN. She's going to be interviewing Io expert Julie Rathbun about observations that are coming to the internet connections near you and what new Io science we can expect this year. Before we get to that interview, I have one last weird bit of news to share. In France, there is a winery whose name translates to Domain of the Meteor. This winery fills an odd depression in the French countryside. As the story goes, there is a 220-meter diameter depression, about 30 meters deep, and the winery proprietors use the scientific hypothesis that it is the impact crater of a meteorite, seemingly long disproved, as a marketing gag for their wine. Although this hypothesis was proposed by several geologists in the 1950s, it was dismissed by acclaimed colleagues a few years later. And then, while on holiday, planetary scientist Frank Becker was caught by the name, gave it another look, and realized that what was meant to be a joke, well, it could actually be a crater. He returned with colleagues and looked for evidence one way or the other. It turns out they found all the dark-colored layers of schists, all the shocked rocks, and all the other things that say, yes, something impacted there. With the help of and I quote, strong magnets attached to a plate, the researchers also found tiny iron oxide bits that look like they came from a meteorite. So, what started as a marketing ploy turned out to be a scientific truth. I feel like this is as close to pigs flying as we're gonna get. And I'm now going to hand the show over to Beth and see if I can order this wine to the American Midwest. We'll be right back.
Thank you, Pamela. I'm joined now by Dr. Julie Rathbun, a senior scientist at the Planetary Science Institute who, like me, loves Jupiter's moon Io. She's here to talk to us about recent and upcoming flybys of Jupiter's moons by the Juno spacecraft and what recent observations of Io's plasma torus might mean for that mission and the future JUICE mission. Thank you for joining me, Dr. Rathbun.
Oh, thank you for having me. Glad to be here.
So glad to have you back. So tell us a bit about what you research when it comes to Io.
Volcanoes. One word, volcanoes. And actually maybe I can definitely elaborate on that. Active volcanoes. I am much more interested if a volcano is erupting or recently erupted, about to erupt, something like that. Then I have a running joke in my head that other folks who study volcanoes, they're really studying volcanic constructs. The mountains, the things that are made. I'm interested in the volcano, the hot, molten liquid rock as it erupts from underneath. How does that happen? How does that work? And of course, Io has so many active volcanoes, hundreds at any one time. So figuring out which one's going off, why, how that might affect others is really what I'm trying to understand.
There's a really great image from the Jerem camera that went around recently that just shows all of these dozens of hotspots on Io's surface. Little red, it looks like a black circle, which is red pock marks everywhere. It's amazing. And I have to admit, made me very happy. I'm sure it made you very happy. So how does, say, the volcanic ash potential, I mean, or what kind of ash is Io giving off? It's not, is it, how is it similar and how is it different sort of to say like an Icelandic eruption or, you know, a stratovolcano eruption?
Very different. It's much more similar to what we on Earth call hotspot volcanism. Something like Hawaii would be much more similar than something like Mount St. Helens. A lot of that ash material is formed, its basis has to do with water.
Mhm.
So you need to have water to interact with the rocks and really in order to give you ash. Um, a volcano like Hawaii, a little anti-intuitive since Hawaii is an island, but that volcano, the magma, the hot liquid rock is coming from much deeper down than where the water is, and it doesn't really have a chance to interact with any water as it's rising to the surface. So that's what we're thinking of the Io's volcanoes like. There's no water on the surface of Io. Io
Mhm.
is not the right temperature for liquid water. Any liquid water it once had has been lost to space. It does have some interesting frost, sulfur dioxide frost on the surface. So you don't get ash the same way you do on Earth.
Mhm.
You get these volcanic flows like you get in Hawaii, and you get venting of sulfur and sulfur dioxide from the volcanoes that is erupted outward. So there's a famous image from the New Horizons spacecraft when it flew by Jupiter, I would say 2007. And
Um,
it's got this plume of material coming off the side of Io, uh, hundreds of kilometers high. You look at the image, and it's coming off so high, you can really see it really well. And there's a great movie of it. And that's what you get from the sulfur and the sulfur dioxide.
Explain to our audience, for those who might not understand, just why Io has this kind of volcanism at all, being as it doesn't have plate tectonics like our planet does, but yet is super volcanic.
Yeah. So it's actually it was such an interesting story. I'm so fascinated by this story. Um, because in the early 1970s, there was this assumption that, and it's not even an assumption, it's a good physical reason to assume that heating the interior of a body, of a planetary body, equals some sort of activity. Volcanism, tectonism, whether it's plate tectonics, different forms of tectonics. And the warmer your body is, it needs to release that heat somehow. And that will
Mhm.
come out through moving around the surface, whether it's tectonically or volcanically. And the heat source on Earth, we think of, there's really two heat sources: radioactive decay and the remnants of planetary formation. Well, if those are the only heat sources you know about, small bodies should not be that geologically active. Io is the same size as the Earth's moon.
Mhm.
The Earth's moon is not terribly geologically active. So there was this expectation that we're going to get to Jupiter and we're going to look at Io and Europa, and they're going to look a lot like the Earth's moon. They're just going to have impact craters everywhere and no geologic activity. But of course, we got there and saw volcanoes on Io. And so, what the heck is the heat source? We know we needed heat. And it turns out that the tidal interactions between Jupiter, which is so large, and Io, Europa, and Ganymede, which are locked in this orbital dance that keeps them in this organized movement, those tidal interactions cause internal heat. It's frictional heating. So every time Io goes around Jupiter, it's squeezed a little bit. And all that squeezing of rock eventually produces heat, and that heat has to go somewhere. and it's pretty extreme. Jupiter's really big. And so you get not just volcanoes, not just geologic activity, but lots of volcanoes and lots of geologic activity.
So one of the really fascinating discoveries that has come out of Juno and Hubble has been the fact that Io's eruptions, which we've established do not give off ash like Earth eruptions do, but they are having an impact on Jupiter itself. These particles are getting swept up and they are causing an aurora. Can you explain the process and how this works?
I can try. I'm not a magnetospheric physicist, but I can see what I can do. So my understanding is that there are folks who specialize in studying magnetospheres, and Jupiter has one of the most interesting magnetospheric systems in the solar system. It's a huge body. It's got large moons that are interacting with it, and it has some interesting phenomena. Um, there's also a ring of material called the Io torus that is composed of charged particles. So this also interacts with the magnetosphere. And we've known about the Io torus for, I think since Voyager days, about as long as we've known about Io's volcanism. And so there's always been this question, where exactly does the torus come from? And well, it makes sense. You've got a volcanic moon, you've got a ring of material, must be throwing some material up, and it ends up in a ring which is orbiting Jupiter. Okay. And we've understood it at that level for 50 years. However, really tying down, okay, how exactly does that happen? Eruption throws material up, like this image of Tavashtar I mentioned from New Horizons. Okay, some of that material rains back down, but not a lot of it, because Io has a very small gravitational field. So a lot of it just escapes from Io. Well, if it escapes from Io, Jupiter has a huge gravitational field. It's not going to escape from Jupiter, so it's going to end up in orbit around Jupiter. So that's probably how we get the Io torus. We also have known for a while that the plasma torus changes in brightness. And it depends on exactly what you're looking at within the torus. As you know, astronomers really like to look at, specific species or specific chemicals when we're looking out. So one of the things that is often looked at around Jupiter is sodium, the sodium cloud. And increases in the sodium cloud's brightness seem to happen every once in a while. So we're wondering, can we connect the dots? Can we see a volcano erupt? Can we see an increase in sodium or some other property of the torus, and actually completely understand that pathway to get from point A to point B? And so far, we have not been able to do it. I've actually been working with a few of these magnetospheric physicists, astronomers who look at the torus and the sodium cloud using telescopes here on Earth. And they look, and then I look at the volcanoes, and we try to say, oh, something just happened. Did you see it? And problem with observing from Earth is there's weather issues. You're sharing the telescope with other people, and so they might be looking at that time. And we've had some of the worst luck. Every time one of us calls the other, it's like, oh, yeah, I missed like 2 weeks because of weather, or yeah, I didn't get time on that telescope just for that 1 month. So we haven't been able to completely nail down the connection. So the details of how that process happens, we still don't understand, and we're trying to find out. And the Juno spacecraft, since it's in orbit there and it can see close up what's going on, we're really hoping we can figure this out while the spacecraft is still there.
That brings me to sort of more recent events. Juno, of course, is in its extended mission and has been doing flybys of the Galilean moons, which of course is just awesome. And it flew by Io. It had close flyby in December of last year. And one of the things that sort of coincidentally happened was Jeff Morgenthaler, a senior scientist also at PSI, has a telescope called the Io Input Output Observatory, IO, love the name. And he actually observed a brightening of this plasma torus in December, between September and December. So do we have any information yet coming back from Juno that might explain what's happened? Or are we still sort of in that waiting period of, please let us have gotten the observations that could match these events together?
So there's two answers to that. One is that when I said I work with some magnetospheric physicist, Jeff Morgenthaler is one of the people I work with, and we're calling each other up from time to time. Yes, did you see something? And he informed me around December, yes, of this what he saw. It said, I think you would have seen something around August if there was a volcanic eruption. And so I looked at the data we had from the infrared telescope facility in Hawaii, and unfortunately, for various reasons, we did not collect data in August, and so we can't do that. Now,
Oh
did
no.
Juno manage to see a volcanic eruption? Unfortunately, well, it's not that unfortunate. For very good reasons, the data is not available immediately for other folks
Right.
to look at. So I have not had access to the most recent GEOROM data. And so I haven't been able to see which volcanoes were erupting. And I'm not even sure what data was collected because
Mhm.
it would have had to be around August, September timeframe in order to have seen it.
Well, I love this moon. It is my favorite moon. I admit to it. And I'm always happy to talk to you about Io and Juno in particular. Are there any upcoming projects that you're looking forward to that you want to tell us? You can tell us about?
Well, I'm also working with a graduate student to look at the GEOROM data. One of the coolest things about the GEOROM data, I mean, it's new, which always, makes things cool. Um, but most of the spacecraft we've sent to the Jupiter system orbit Jupiter in the same orbital plane as the moons. What
Mhm.
that means is Io's poles you do not get a good look at. Juno was specifically designed to study Jupiter's poles. So it's in a polar orbit, goes over Jupiter's pole every time it goes over. As a result, you do tend to get better looks at Io's poles also. So
Right.
I am very excited to see there's been some evidence from previous observations, both from the ground and from previous spacecraft, that there are fewer volcanoes at high latitudes, fewer volcanoes near the poles. Is that real, or is that just because we didn't get a very good look at them? And so I'm really dying to find that out. And then there's also evidence that the volcanoes might be a different kind of volcano near the poles, which is another thing I'm just really looking forward to finding out. So I've got a graduate student who's been looking at the GEOROM data. She's gotten through, I think, the first 6 or 7 orbits. Her name is Madeline Patine at Cornell University, and just we're still waiting to see what the results are because we're trying to build up. Every time you look, every orbit, you're looking at a slightly different part of Io. So we have to
Mhm.
wait until she gets through a certain amount before we get a global
Mhm.
picture. So I'm really, really excited to see what that looks like.
I will look forward to when papers come out on that and your findings. So I'm very excited for you as well. Thank you, Dr. Rathbun, for being with us here today, and good luck in your research. And thank you for providing me with a lot more of my IO love that I'm allowed now to give out. So
I'm
thank you for
always
joining
happy
us.
to share the Io love. It was fantastic.
All right, have a fabulous rest of your day.
Thank you.
Thanks, Beth, for that great interview. I look forward to future guests. And I also look forward to dark skies. Those of you living in high latitudes, such as in Canada or South Africa, may have noticed the sky lighting up with aurora more this year. This is completely normal. Our sun has an 11-year cycle during which it goes from quiet to active and back to quiet again. The last active period or solar maximum was in 2014, and the next is predicted for 2025. Our current solar cycle is the first to take place since companies like SpaceX started launching small, low Earth orbit communication satellites. And one of the great questions is just how many satellites will get harmed during solar max. When the energy from the solar flares hits the Earth's atmosphere can expand outward, causing spacecraft to experience more drag. SpaceX already lost one set of 40 Starlink satellites in February 2022 when a solar storm hit. Since we don't know when solar flares and storms may happen, we can't easily avoid launching before they occur. If you want to find out if there are aurora and possibly dead satellites in your future, check out spaceweather.gov or for more far-flung coverage, spaceweather.com. In addition to the new constellations in low Earth orbit, this solar max is also the first since distributed sources of renewable energy started to play a major role in supplying the power grid. It turns out that when the Earth's magnetic field oscillates under the impacts of solar particles, the oscillating magnetic field generates current in power lines. This can actually overload circuits and cause power outages in a variety of ways. This problem was responsible for the March 1989 9-hour power outage in Quebec and some surrounding areas. This kind of power outage can be deadly, especially in winter when it affects heating. That particular outage affected systems powered through Hydro-Quebec's electricity transmission system, which is a fairly simple system with not a lot of inputs as far as power systems go. Things get more complicated as you add on today's wind and solar power and the associated battery systems. Recognizing the increased complexity the power grid faces, the National Science Foundation has funded University of Oklahoma researcher Paul Moses to explore the gaps in our current understanding of what could happen and what we need to watch for. As Moses explains, quote, "A lot of the components in our power grid are based on century-old design principles, like the transformer, which is the device that changes voltages. The transformer is everywhere, and it is not going away for decades to come. So we're stuck. We're stuck in a way with these legacy components. We want to learn how they respond to this renewable energy-rich environment coupled with all these disturbances like geomagnetic storms that presents new burdens and stressors. When you have solar, wind, and battery storage, it has to be connected to the grid through what we call inverters or solid-state power converters. How does this new technology associated with renewables work with old technology, the archaic infrastructure? The grid fundamentally was not designed to operate with these devices, so it raises new uncertainties." End quote. Solar max is one of those times every astronomer approaches with a certain level of joy as we wonder just how will this sun misbehave this time? And what amazing solar storms and aurora will we get to see? I truly hope this cycle is one without major damage to spacecraft or power grids, and also one that puts on the kind of light show we can all enjoy. And speaking of spacecraft, next up, I'm pleased to welcome on aerospace correspondent Eric Mattis for this week's Tales from the Launchpad. Hey, Eric.
Hi, Pamela. As we mentioned earlier in the year, 2023 will see many new rockets conduct their inaugural flights. Two of them attempted to do so this past week, Mitsubishi's H3 and Relatively Space's Terran 1. Built by Mitsubishi, the H3 was supposed to debut in February, but the first launch attempt was called off at the last second after ignition of the liquid-fueled engines, but before the solid rocket boosters ignited, due to a problem with the engines. After a couple of weeks of troubleshooting, a second attempt was made on March 7th. Most of the count went well. There was the standard second-by-second count for the last 5 minutes, common in all Japanese launches, but then the big rocket lifted off from its coastal launch pad and turned toward space, carrying Alos 3, a new weather satellite. Everything looked nominal until it didn't. The huge first stage and its 3 brand new engines worked perfectly, but after engine cutoff and separation, Mission Control could not confirm that the second stage engine had successfully ignited to take the satellite the rest of the way into space. A day later, the Japanese Space Agency, JAXA, released a preliminary analysis of the rocket's telemetry, which revealed the flight computer sent a command to ignite the second stage, and the separate computer controlling that engine did receive the command. However, the valves that control the flow of propellant into the engine did not open, so the command to activate the flight termination system was sent about 14 minutes after launch, by which point the vehicle had started heading back to Earth and it was clear the mission was lost. As of press time, the cause of the electrical fault in the engine controller is unknown. The new controller was developed specifically for the H-3 rocket. This means that the LE-5B engine, which is a proven design, is probably not going to be subject of a large-scale investigation. After the failure, some in the Japanese space industry, including former JAXA astronaut Soichi Noguchi, questioned why the first flight of a new rocket carried a major weather satellite. The satellite, Alos 3, cost 38 billion yen, or around 250 million US dollars. Its loss leaves JAXA without a civilian satellite offering a high-resolution cartography capability. According to JAXA, the risk was justified because a similar launch, the first H-2B back in 2009, had worked. That launch had also carried a real payload, an operational H-2 transfer vehicle, or HTV. Japanese Prime Minister Fumio Kishida has announced that a failure investigation team will be set up and reminded everyone that, quote, success is the result of many failures, end quote, and that he, quote, respects the efforts of everyone involved and looks forward to the next challenge, end quote. The other inaugural flight, that of Terran 1, built by Relativity Space, was originally set for March 8th. Terran 1 is the first orbital rocket that is largely 3D printed. Relativity Space says that this approach reduces costs by simplifying the supply chain and decreasing the number of parts in a rocket by 100 times. Unfortunately, Terran 1 didn't manage to launch during its 3-hour launch window on the 8th. Several attempts were made, but it appears that the rocket's ground system was not keeping the liquid oxygen at the correct temperature, so the decision was made to scrub the launch attempts for the day. Not launching and being able to try again another day is better than launching and wishing you hadn't. As of when we're recording this, the next attempt is set for the day this episode airs on Now Media TV. We will have an update for you on how Good Luck, Have Fun went, along with the SpaceX launch for OneWeb that happened just before we recorded this episode in next week's show. And now, for some statistics for a few of the things that are in orbit around the Earth. There are 11 toilets in space, 4 on the ISS, 2 on the Tiangong space station, 1 on Shenzhou 14, 1 soon to be returned on Soyuz MS-22, 1 on Soyuz MS-23, 1 on Crew Dragon Freedom, and 1 on Crew Dragon Endeavour. We keep track of orbital launches by launch site, also called spaceport. According to RocketLaunch.live, so far this year, the USA has had 17 launches, China 7, Kazakhstan 3, Japan 2, and India, the United Kingdom have each had 1. Of these 31 launches, there have been 3 failures, reminding us that space is hard.
Thanks, Eric. Before we go, I would like to share what may be my favorite science headline of all time. According to the Jerusalem Post, corgi-sized meteor as heavy as 4 baby elephants hit Texas. NASA. My first year as a journalist, I learned there is a long-held tradition of trying to sneak interesting analogies into articles. And the items in those analogies furnish an imaginary journalist's home. It's unclear if this headline comes from author Aaron Reich or from one of his editors. To whoever wrote this amazing turn of phrase, your journalist home now contains a corgi and 4 baby elephants, and I salute you. But the fun doesn't end here. While trying to reverse engineer just how big a corgi-sized meteor might be, astronomers took to Twitter and to their keyboards to assess just how large your typical corgi, assumed to be cylindrical, might be. The answer, without correcting for ear size, appears to be 25 inches long and 11 inches in diameter. Moral: Americans will measure in anything except metric. Corgis are cylinders, cows are spheres, and math is better done with friends and animals. And that is it for tonight. Good night, everyone, and remember to go out and look up.